Hey folks, welcome to our first lecture for topic 2, DC circuits. Hi everyone. I'll try to check in and show you a video of me every now and then just to kind of keep this personable and keep it human. There is a face behind all of these recordings. So let me go back to sharing my screen here. Okay. So topic 2 is really where we start looking at our circuit work and building circuits and talking about circuit elements like resistors. We're going to start with resistors and then move on to capacitors. So like resistors and uh, power sources and looking at Ohm's law in action, right? What happens when we put a lot of resistors into our circuit and why? Why would we want to do that? So the first thing we notice is that this topic is called DC circuits, right? Direct current circuits. That's because we have two ways really of receiving or sending current. And the first way we're going to talk about is DC current. So a direct source of current. You get a steady flow of current all the time. And that's what you get from your batteries like a Duracell battery, like an Energizer battery. It's a constant flow that is very steady all of the time. And the flow of electrons is from the negative terminal to the positive terminal through the wire. But remember that in physics, as we follow the current, we always have it coming out of the positive side of the battery. We'll talk about that today. Towards the end of the semester, we'll talk about AC current, so alternating current. And that's what we get when we plug into a wall socket in any building. And what that means is that the current is actually alternating. It's a sinusoidal delivery of current so that it's fluctuating. The direction of the current, think about a sine wave, right? So a sine wave has the current, let me see if I get my pen on. The direction of the current is actually sinusoidally and being delivered from positive to negative, from positive to negative through zero. And in the United States, it's doing that at 60 hertz, which is, it changes direction 60 times per second. So we'll get to that much later in the semester, but let's really focus on our DC current. So the equivalent of connecting to a Duracell battery and getting a constant source of current. And yes, you can take a minute here and sing a little AC/DC if you want. I'll never say no to that. Okay, so let's get some vocabulary taken care of, right? We want to talk about current and we want to talk about voltage. And so we want to make sure that we have the appropriate vocabulary to kind of bring all of that together for us. So the first thing is we want to understand what is it? What is the source that is supplying the current? What is current? Current is moving charge. So what is it that's making those electrons move? Well, we're going to call it the electromotive force, EMF, and we're going to use the Greek symbol, okay, curly E. So electromotive force is a very general definition that says the force that makes the electrons move. Well, in practice, what is that electromotive force? Well, it can be a battery, right? Like your Duracell. It can be a generator, which we'll talk about later. It can be many things. So this symbol E, curly E, is basically our symbol for battery. It is what is making the electrons move. So we want to be able to kind of move between our two symbolisms for it. E, which is very general. It could be a battery, but it could be something else. And delta V specifically when we're talking about now like a battery, like a Duracell battery. Okay. So this electromotive force, or battery, is, that's like a charge pump, forces the electrons to move. If we want to go back to our analogy of water flowing through a pipe, that charge pump, the battery, is like a waterfall. There's a high side and a low side, a positive terminal and a negative terminal. So remember that in our batteries, we have all this chemical reactions that physically separate the electrons from the protons. Now they want to come back together, but they can't inside the battery. So they have to flow out of the battery all the way around to come back to the other side. And then inside the battery, they get separated again. So we can think of this as our waterfall. So a 9-volt battery pumps 9 volts into the circuit and maintains the current steady at those 9 volts, right? So we've looked at the units of volt as a joule per coulomb. So we've seen something like this bottom drawing before. It's our water analogy. So our battery, think of it as moving the water up the fall. Now it wants to fall down, right? The water itself wants to fall right back down. Let me find a good color here. The water itself wants to fall back down, but it can't, because that's what the battery does. It physically separates it, doesn't allow that to happen. So instead, the water, so our battery, I'll call this E, our battery, pumps the water uphill. Then it flows around, and then it can fall back down through any of these branches. Okay. So what we want to talk about is the difference between what is called series and what is called parallel. So a series circuit and a parallel circuit are going to behave differently in terms of their properties. Connecting resistors in series gives me a different result than connecting resistors in parallel. So I'm going to talk about each of those, but remember that what we're really thinking about is a battery as a water pump, taking stuff up to the top of the waterfall, and then it wants to fall down. So if I connect my resistors in series, what I can think about is there's only one path for the water to flow. The water's up at the top of my waterfall, and it can only follow this path to come back to the bottom of the waterfall, to have the battery separate them again, come back up to the top, and repeat and keep doing this continuously. There's only one path. Think about it as only one tube, one pipe for the water to flow through. But in that pipe, there are three, in this case, three separate resistors impeding its flow. If we look at a parallel circuit, okay, so for a parallel circuit, we still have our battery pump here, our battery. So the electrons come up to the top here. They want to fall back down, but they can't. So they come around, and now the difference with parallel is we have options. We can have some of our water flowing through this first branch. We can have some of the water then continuing through the second branch. there's different paths, and then they come together and we get the same flow back. Come on, blue. There we go. So the blue comes, but then there's what we're going to call a junction. So our junction points right here, the junction points, splits the water, splits the current. Some of it will go through branch A, and some of it will continue on through branch B, but then they come back together and we get the total current again. So in series, there's only one water pipe. There's no options for the water. Now, if we think about water now in terms of current, that means that in series, they all have the same current flowing through them, the same amount of water. The water has nowhere else to go, but to pass through resistor 1, through resistor 2, through resistor 3, the exact same amount of water. In our parallel circuit, what happens is the water comes through this, comes out through here. Oop, I should have done that blue. Hold on, my iPad's acting up. Sorry. Think you better get used to my iPad acting up. Okay, so the water comes through, but now there's a junction, right? So some of the water will come through the first branch, but another separate amount of water will come through the second branch, over here, branch B, and then they'll all come together again back into blue. So think about, there's a junction, a split. The pipe splits into two, and some water will flow through pipe A and some water will flow through pipe B. So that's the main way to think about circuits. The first thing we want to do is we want to identify if our circuit elements are in series or in parallel. And we're going to talk about ways for testing whether things are in series or in parallel. Now, in an example like this, it might not be that difficult to see what is series and parallel, but as we move through our semester, for example, and we start getting into more and more complex circuits, well, what's in series and what's in parallel, right? Okay, so let's take it step by step here. Here we go. Where was I? I was right here. All right, so let's talk about resistors in series first, okay? So there's only one pipe. The same amount of water is flowing through element 1 as is flowing through element 2. Right now, we're only talking about resistors, and remember that our light bulbs are a type of resistor, okay? So resistors and bulbs are basically the same thing. So we have our battery with our positive side and our negative side, and all the current flows through bulb 1, has nowhere else to go, must flow through bulb 2 and come back. There's no split, there's no junction. So the same charge is flowing through both bulbs. Now let's look at our circuit diagram. We want to draw this, instead of having to draw out an actual battery, right? We denote it with our battery symbol, with the long side being the positive and the short side being the negative. When we do it this way, this means that the current flows out the positive side, up this way, to the right, and back down. And so you can see that they've shown the arrows that correspond to the direction we have chosen. Out the positive side and into the negative. Now, they're all going to have the same charge, therefore the same current. So the current is going to be the same for all the resistors. The water can't go anywhere else. The same amount of water has to pass through both resistors. So the current is the same for all resistors in series. And what happens, so for the current, we know that the current is the same. But we want to know what happens to the resistance. What is the actual resistance? What happens when we put two resistors in series like this? Why would we want to do that? Well, what we find is that resistors in series add their resistance. In other words, resistor 1 and resistor 2, when placed in series, make the total resistance of the circuit stronger. So if I want larger resistance in my circuit, I'm going to place my resistors in series. And the equivalent resistance is going to be the sum of all the resistors placed into it. So when we look at circuits, in our circuit diagram as is, what we want to do is we want to be able to go from a diagram with multiple elements and reduce it into a diagram with one single element. In other words, these two resistors are equivalent to one resistor. And I find that by adding the two together. The power source, the voltage, is going to stay the same because I'm not doing anything to the battery. And I'm going to use Ohm's law to understand what all of that circuit looks like. Now, again, doesn't seem too complex for our simple circuits, but when we get into circuits, say like this, and I want to know how much current is flowing there, well, that's a little bit more complex. So I want to be able to work with my circuit and reduce it into one single element, one resistor, one battery, one current, and work from there. We'll see how all of that pans out for us. Okay. So Ohm's law is going to be, used in all of this, resistors in series and resistors in parallel. The difference is how those resistors behave and how the current behaves. Okay, so let's focus on series first, right? Resistors in series all have the same current. Water cannot go elsewhere, so however much flows through resistor 1 must also flow through resistor 2, must also flow through the resistor 3, right? So the same water or current has to flow through each element in that branch. So let's do a quick example, okay? Now, resistors are pretty much made in mass production. And you go to Radio Shack. Oh wait, I don't think Radio Shack exists. Shoot, I think I'm showing my age. You go to, where do people go now? Fry's Electronics? Circuit City? Do any of those still exist? You go to your local electronics shop and you purchase resistors, usually made in standard denominations. So you need to work with, if you want a different resistance than what is available to you at the store, well, you want to be able to combine your resistors in series and in parallel to get the desired resistance for your particular circuit or your particular branch. As our circuits get more and more complex, we might want, a specified amount of current in one branch of our circuit, but a different amount in another branch of our circuit. So we want to use our resistors in ways that give us the desired results. So that's why we use resistors in series and in parallel, to give us the desired results and still be able to use mass-produced resistors. And they're about a dime a dozen. Okay, so let's start with our first example here, where we have 4 resistors arranged as shown. So I think in this example, it's a little bit obvious that it is a single loop, a single branch. There's nowhere for the water to flow, and everything that passes through resistor 1 will pass through resistor 2, resistor 3, resistor 4, so on and so forth. So the water is going to flow out the positive side, the top of the waterfall. Okay, so remember this is like the top of our waterfall over here. This is the positive side and the negative side. Okay, so water flows out the positive side and into the negative side. Okay. So it goes out the positive side, over here, has nowhere else to go, just turns a corner, but it can't leave. All the water must flow, pass through 1, pass through 2, pass through 3, pass through 4, and then come back into the bottom of the waterfall, the negative side. But what I want to know is, when all of these resistors, all of these obstructors are in the way, what is the actual current and resistance flowing through this branch? So the first thing I need to do when I see a circuit with more than one element, the very first thing I need to do is I need to reduce it to a circuit of one single element. In other words, the equivalent. And once I have that, I may then apply Ohm's law. I may not apply Ohm's law until I reduce my current to a single element. So I cannot use Ohm's law until I have successfully reduced my circuit into one single current. Sorry, one single resistor. All right, so let me get a whiteboard up here. Come on, work with me. All right. So let me get a whiteboard here. Okay. So let me redraw my circuit. It's good practice to redraw these circuits. Okay. What I have is resistor 1, resistor 2, resistor 3, and resistor 4, all in series, coming back to a battery with a positive and a negative. Okay. So let's see, we've got R1, R2, R3, R4, and we have our battery here. All right, so if resistor 1 had a value of 2 ohms, resistor 2 had a value of 4 ohms, resistor 3 has a value of 5 ohms, and resistor 4 has a value of 7 ohms, and it is connected to a battery of 6 volts, and yes, we could call that the EMF. So the first thing we want to do is find the equivalent resistance. And the next thing we want to do is we want to find what the current is if the EMF in the battery is 6 volts. Okay. So to find the equivalent, the first thing I need to realize is that everything is in series. Okay, so let me get a new board. So the equivalent is I just add them all together. Simple enough. R1, R2 plus R3 plus R4. Okay, so I add up 2 plus 4 plus 5 plus 7, and I get an equivalent resistance of 18 ohms. So I went to the store and they didn't have an 18 ohm resistor, but they had a bunch of 2s and 4s and 5s and 7s, so I know that I can grab them and combine them to get my desired result. Now that I have the equivalent resistance, each of these resistors behave like a single 18 ohm resistor. Now I can write my useful circuit. Okay, so now this is my equivalent, which is 18 ohms. And this, I can go ahead and call it my equivalent, was 6 volts. It hasn't changed. It's the original battery, and we're not really going to combine batteries until we get into Kirchhoff's rules, but that's a whole other thing. So we're not really going to combine batteries. So once you have it down to one single circuit element with one single battery, now we can use Ohm's law in terms of all of the equivalents. Delta V equivalent is equal to the current equivalent times the resistance equivalent. Okay, so we're looking for the current flowing through this. So the current flowing through this is going to be the voltage over the resistance. So it's a 6 volt battery and the total resistance is 18 ohms. So this is going to give us a current of 0.3 amps. And there's only one current, right? Even if I go back and look at my actual circuit with 4 resistors and a battery, there's still only one current. There's nowhere else for the current to go. The same amount of current that flows through here, flows through here, flows through all 4 of the resistors, and flows back to the bottom of the waterfall. There's no other choice. It is the current that flows through everything. Okay. All right. So then, hi. All right, let me go back to sharing. Okay. So we found the equivalent resistance, 18 ohms, and we found the current in the circuit. There's just one current, and it was 0.3 amps. Okay. Another way to combine resistors or circuit elements is in parallel. So this is going to be a little bit more tricky, but remember that with parallel, we really talk about having 2 branches for the water to flow through, 2 bulbs, right? So we're thinking about our battery. We're thinking about our battery pumping the water up, and then the water flows, but now there's a junction so that some of it flows through a branch like this way, but some of it continues on and flows through this branch. So there's going to be different currents. There's a different amount of water flowing through here than is flowing through this middle branch, than is flowing through this branch. They all have different amounts of current. So it gets a little bit trickier. So let's go back. Okay, first, let's see how we identify when resistors are in parallel. So in parallel, there's a way to test for it, okay? But first, let's talk about what parallel means. Parallel says, hey, I've got a battery here. Here's my battery. I'm looking at this drawing. Here's my battery, positive side, negative side. And the electrons want to flow, right? So from the top of the waterfall, and they want to make it down to the bottom of the waterfall, but they have to go around. So the electrons flow through here, but then I have a choice. I can either, flow through this little thing, or the water can continue and flow through this thing. Oop, wrong color. Water can continue and flow through this thing. Back. So these are all individual pipes, right? There's a junction, there's a split, there's a point where a choice is made. So if I first of all, take a battery with two resistors like this, and I want to draw a circuit diagram, while I replace my battery with my battery symbol, the long side with positive, the small side with the negative, and I start following the current around. So it comes out the positive, okay, comes this way. So here we see it just says I. But then there is a junction. This junction is a split. That current I, some of it is going to flow through resistor 1. Some of it is going to keep flowing through resistor 1. So now I call it I1. Through resistor 1, back over here. And some of it is going to flow through resistor 2, this way. And I call that I2. They're eventually going to meet back at my other junction. They're eventually going to meet back at my junction here and flow the same amount of current back. I don't lose any water along the way. Whatever leaves must come back. It just splits along the way. So what I get is current that now I have to specify. What is the current flowing through resistor 1 versus what is the current flowing through resistor 2? When we were talking about series, we didn't have to ask that. We just said, what is the current? Because it was the same throughout. But now what happens is there is something they share. So in series, they share a current. They all have the same amount of current flowing through it. Well, what about in parallel? What do they share? Well, I'm going to give you the answer. They share voltage. So think about, let's come back to our water analogy here. And think about the pump here, the water pump. The water pump is like a waterfall, right, of a certain height. Well, each of the branches have the same height that they're going to fall through. I just have less water through each branch. Look at how many little dots, each one of these representing positive or negative, it doesn't really matter, representing a moving charge. And then some of them, there's only 2 of them that go through here. And there's a little bit more maybe that come through here, but they all have the same height. Everything has the same height. Everything has the same delta V, the same voltage drop in each branch. So the same delta V is going to flow through both. Another way to think of it is resistor 1 is fully connected to the battery. It's getting the full connection to the battery. And likewise, resistor 2 is perfectly connected to the battery. It's getting the same voltage as the battery. When I draw it as a circuit diagram, I see that resistor 2 completes its own loop here, its own loop with the battery, so it gets the full battery. And that resistor 2 completes a full loop with the battery. It gets the full battery, the full delta B. So one way to test, well, no, let me back up on that. I'm not ready for that yet. So one of the characteristics of our resistors in parallel is that they're going to share a voltage. They're not going to share a current. The current's going to split, right? In this case, they're going to split at point A and come back together at point B. So how it splits depends on the path of least resistance. More current will travel through a path with least resistance. So now how it splits depends on the values of R1 and R2. A lower resistor will have more current, such that current is conserved throughout the circuit. So whatever comes out of the battery on the positive side must come back into the battery on the negative side, but it does split. So that split is called the junction rule. Whatever current flows into a certain junction has to equal the current that flows out of a certain junction. So if I look at this junction A here, this is point A, I'm just looking at this. What I have is current 2 flowing to the right in this middle branch out of that junction. Current 1 flowing up this way out of that junction. But the full current, the total current before the split, which we just call I, is flowing in to the junction, right? I is coming into this point, 2 is leaving it, and 1 is leaving it. So I in equals I out tells me that the current before it splits must equal 1 and 2 combined so that I conserve current. I don't lose any, it just splits, and it splits in such a way that whatever comes into the junction is what goes out of the junction. So voltage is the same for both of these elements. The current's going to split, and how it splits depends on the resistor. But what happens when I take two resistors like this and I combine them in parallel? What does the equivalent look like? Right? Remember that I'm trying to create a circuit diagram that I can work with that has one equivalent resistance. So for resistors in parallel, it is a 1 over summation. The resistance is going to decrease. The equivalent resistance is going to be smaller than each of the resistors that I started with. So if I go to the store and there's only a 100 ohm resistor, but I need a 50 ohm resistor, well, I can take 100 with another 100 in parallel and create a 50 ohm resistor, reduce the resistance. Okay, so again, we want one equivalent resistance with our voltage in order to use Ohm's law. So we're still going to use Ohm's law. Okay, so how do I test to see if resistors are in parallel? Well, what I need to do, and again, it might not be so important right now, but what about when I have something like this? What's in parallel and what's in series? Okay. So what I do to test for parallel, same here, what's in parallel, what's in series? To test for parallel, whoops, wrong way, sorry. To test for parallel, what I do is I say, okay, let's look at each one of my elements. Let's start with resistor 1. Resistor 1 has a left side and a right side. Resistor 2 has a left side and a right side. I want to make sure that both of their lefts, actually, let me do this differently. Let me do left sides both as black and right sides both as red. Okay. What I want to do to make sure that they're in parallel is I want to make sure that both of their left sides can flow uninterrupted to the same side, to the same location, I'm sorry. And it doesn't really matter which location you choose. I could choose point A as a location. So I asked myself, can the left side of resistor 1 flow to location A uninterrupted? In other words, there's not another element in here. Can the left side of resistor 2 flow to point A uninterrupted? The answer is yes. So far, they seem to be in parallel. Now I need to do the same with the right-hand side. I also need to say, let's see now, maybe we want to flow it over to a random point over here. It doesn't really matter where. Can the right side of resistor 1 flow uninterrupted to that point? Ooh, I don't know what that was. Flow uninterrupted to that point? Yes. Can the right side of resistor 2 flow uninterrupted to that point? Yes. Both their left sides and their right sides are able to flow to that same point without encountering another element. They are in parallel. So as our circuits get more and more complex, you really do want to make these checks. Wait, what's in parallel? What's in series? Sometimes it'll be visually obvious and sometimes it won't. Okay. So let's do an example where they're in parallel. Now this looks vastly different than the other one, right? So here is our positive side and our negative side. So if we follow our current around, it's going to come out the positive side this way into the over here. But wait, now we have a junction. So some of the water is going to flow through the 3 ohm resistor. Some of the water is going to flow through the 6 ohm resistor, and some of the water is going to flow through the 9 ohm resistor. Keep flowing this way. This current has one pipe to go through this way. This current has one pipe to flow through this way. And then they all come together again and flow back so that the same amount of current, the one that I'm calling red I, comes out of the positive side of the waterfall into the negative side of the waterfall, the top of the waterfall to the bottom of the waterfall. I didn't lose any water or current, it just split. Some of it goes through the 3 ohm branch, some of it goes through the 6 ohm branch, some of it goes through the 9 ohm branch. Then we want to test if this is actually in parallel. So now I say, can all of their top sides, can they flow uninterrupted to the same spot, say to spot A? Well, let's see. Can it? Yes. Can it? Yes. Can it? Yes. So far, all of their top sides are good. What about all of their bottom sides? Can all of their bottom sides flow uninterrupted, say, to that point? Can it? Yes. Can it? Yes. And can it? Yes. So check and check. They are in parallel. When would it not be in parallel? Well, imagine that we have maybe an extra resistor right in here. In that case, you'd have to do something else, because the top side could flow to point A uninterrupted, check, but the bottom side, oh, it hits an interruption, cannot flow uninterrupted to point B. And if I choose to look at the bottom sides, I would find the same kind of argument. I would say, hey, the bottom side of this makeshift resistor, sure, it can flow to point B. But the top side of it, oh, it's going to hit another element along the way. It cannot flow uninterrupted. So sometimes it's not going to be visually obvious, and it's important to check. Do all of their top sides flow uninterrupted to the same place? Do all of their bottom sides flow uninterrupted to the same place? If the answer is yes, then they're in series. Okay, so in order to answer any of these questions, the very first thing I have to do is take this circuit with 3 resistors and create what its equivalent would be. What does the equivalent resistance look like? Okay. All right, so let's draw our not our force diagram. Let's draw our circuit diagram. All right. So we've got our battery, positive side and negative side, positive and negative. It has 18 volts. And then we're going to take this point here and we're going to split it. 1, 2, 3. We're going to have resistor 1, resistor 2, resistor 3, and then everything's going to flow back into my battery. Okay, so this is going to be R1, R2, and R3. The total current coming out of this is what I'm going to call I without any subscripts. It's just my total. If I want, I may call it the equivalent. But then we're going to split. I1 will flow through R1. I2 will flow through R2. And I3 will flow through R3 and then back to the equivalent. So our values for R1 is, let's see, oh, that was 3 ohms. For R2 is 6 ohms. And for R3 is 9 ohms. The first thing we want to do, and even if we're not asked, we must do this, is to find the equivalent resistance. Then we want to find the current in each resistor. That means what is I1, what is I2, and what is I3. They're going to be different. And then in part C, we're going to talk about the power to each resistor and the total power. So remember that our resistors can be light bulbs and power is wattage. So this is asking if we connect 3 light bulbs in parallel, what happens to the wattage? That's what part C is asking. Okay, so first thing I need to do is create a equivalent. Okay, so I'm gonna, let me come back. Okay, so what I'm gonna do is I'm gonna take these 3 resistors and combine them in parallel. So combine them in parallel, and as such, get their equivalent. Okay, so resistors in parallel add as a 1 over. So 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, and you can keep doing that for however many resistors you have. So 1 over R equivalent is 1 over, 1 over 3 It's really hard to write on these tablets. I apologize. Plus 1 over 6 plus 1 over 9. So 1 over R equivalent is 0.611. So R equivalent, now I've got to do 1 over 0.611. And we get an equivalent resistance of 1.63 ohms. So look at what happened. 1.63 ohms. It is smaller than any of the resistors that made it up. It was a 3, a 6, and a 9 ohm resistor, and I combined them in parallel to create a smaller resistor of 1.63 ohm. So once I have that, now I can redraw my usable circuit that just has the equivalent resistance and the battery, which I can call equivalent. It hasn't changed. It's the 18 volts. And this is 1.63 ohms. And what flows through this is what we call the equivalent or total current, and it's just 1. So with this, now I can use Ohm's law. So first of all, this is our answer for part A, find the equivalent resistance. But even if we weren't asked, we'd have to do it anyway. Okay, so now for part B, we want to find the current through each one, okay? All right, so in order to find the current for each one, I have to use Ohm's law. So Ohm's law says delta V is IR. Well, if I want to talk about resistor 1 having current 1, then I have to talk about the voltage flowing through 1. And if I want to talk about resistor 2, or 2, then I'm looking at current 2, and I'm looking at the voltage flowing through resistor 2, so on and so forth. So if I want to look at resistor 1, right? Let me come back and see what are the voltages. Here we go. What are the voltages flowing through each of the resistors? Well, they're each individually connected to that 18-volt battery, right? Go back to that water pump slide. The water pump is 18 volts high, and each of those branches has to drop back down those 18 volts. They're sharing a voltage. Go back to that water pump slide. Okay. They're all sharing voltages. What changes is how much water flows through each one. So delta V equivalent is the same as what's going through resistor 1, is the same as what's going through resistor 2, is the same as what's going through resistor 3, and we happen to know that value, and it's 18 volts. Now, we know resistor 1 is 3 ohms. We know resistor 2 is 6 ohms. And we know resistor 3 is 9 ohms. So with that information, we want to find current 1. Well, that using Ohm's law, the current is going to be the voltage through it over its resistance. So this is going to have 18 volts over 3 ohms, and that's going to be a current of 6 amps. What happens with the second resistor? Well, that is delta V2 over R2. So 18 volts over 6 ohms. and this only has 3 amps. And our third resistor, okay, our third resistor has delta V3 over R3, so our 18 volts over 9 ohms, and this has 2 amps. So notice how the highest resistance has the lowest current. Current takes the path of least resistance. The least resistance has the highest current. Also, we're not asked for this, but I would like to do this. So this is the current flowing through resistor 1. It has 6 amps. And the current flowing through resistor 2, right? So we've got the current flowing through 1, check. That's a check mark. We've got the resistor flowing through the current flowing through resistor 2, 3 amps. We have the current flowing through resistor 3, 2 amps. What is the total? What is the equivalent? Well, there's a couple ways to do this. First way to do it is we can look right here at our equivalent circuit. And we can use our Ohm's law with everything equivalent. Delta V equivalent is I equivalent R equivalent. So that the equivalent current is delta V equivalent, 18 volts, over R equivalent, which is 1.63 ohms. And this gives an equivalent current of 11 amps. Okay, so that's one way to do it. Go back to your useful circuit diagram with the equivalent. It's another way to do it. Well, we also know that any current that flows into a junction has to flow out of a junction. So the total equivalent current split up right at this point. Right at this point, right? So that some of it went this way, some of it went this way, some of it went this way. What flowed out of that junction was I1, I2, and I3. What flows in to that junction is I equivalent. So I'm going to draw a new circuit here. This one's getting a little bit sloppy. So let's do this, and then we've got 1, 2, 3, 1, 2, 3, and then they all come back together to my battery. So over here, this is the equivalent. Here's my junction, and comes out I1, I2, and I3. So here's my junction. So what flows in must equal what comes out. So what flows in is my equivalent, and what flows out is I1, I2, and I3. So I can't lose any current. So the equivalent or total must be the sum of the three. So we had 6 amps plus 3 amps plus 2 amps. Hey, the total is 11 amps. Same as we found when we looked at our equivalent circuit over here. Okay, we also found 11 amps. So there's a couple ways to do that. All right, so one more part C. Okay, So now part C says, all right, let's talk about power. Part C says find the power through 1, the power through 2, the power through 3, but also the total. Okay. So remember that power is given in a couple of different ways. We can write it as I delta V. We can write it as I squared R. And we can write it as delta V squared over R. Well, I could really use any of them. I have all of the values. I have V1, R1, I1, V2, R2, I2. But the first one, doesn't require any squaring or dividing, so I'm just going to use that one. So the power flowing through bulb 1 is the current flowing through bulb 1 and the voltage flowing through bulb 1. So that is 6 amps times 18 volts, which gives 108. And remember, the units is a watt, a joule per second, energy per time. My second bulb has I2 delta V2. Okay, so that's going to be, let's see, now we had 3 amps with 18 volts. So that is 54 watts. And the third one is I3 delta V3, and that is 2 amps times 18 volts. And this is going to give me 36 watts. So the total is actually just the sum of that. Power adds for parallel circuits, and we'll talk about that in a second. So I just add those all up, and I get a total power of 198 watts. What's another way that I could do it? I could do the equivalent power, which is the total, is going to be the equivalent current times the equivalent. Right, so what was our equivalent current? We said it was 11 amps times 18 volts, right? So 11 times 18 gives us 198 watts. So same, check, check. Okay. All right, so I think that got us part A, B, and C. And hold on, let me stop this. Oh, that's not what I want. Here we go. Stop share. Hey, all right, let me share again. It's always nice just to check in. Hi, there's a face behind here. I wish I could see your faces. Join me for office hours. Okay, so there we have it. There is the equivalent resistance, the current through each one. I didn't ask for the equivalent resistance, but it's always great to have it. And then the power through each one and the power total. So this is the first of 3 lectures that we'll do on this topic. We will continue next time looking at kind of series and parallel. So actually, let me just, here's a summary of our series versus parallel. When they're in series, they all have the same current because there's nowhere else for the water to flow. It's the same pipe through each of those. And what happens as bulbs are added is that brightness actually decreases. Why? Because the resistance increases. So if the resistance increases, the power decreases. And if one of my bulbs burns or breaks, what's going to happen to my circuit? Now in parallel, right now what they're sharing is the same height of that waterfall, right? Each branch has to drop back down to the ground so they all have the same delta V. And as bulbs are added, actually the brightness stays the same if they all have the same resistance. Sorry, I should add. If every single bulb had the same resistance and I added them, the brightness would stay the same. Why? Because they have the same voltage flowing through them. And what would happen if I remove or burn out one of the bulbs? We'll talk about that. And the resistance actually decreases, and I might have to use the junction rule to figure things out. So when we come back, we'll kind of come back here, talk about answering those questions, look at a three-way light bulb, and start doing some more complex circuits where we have both series and parallel pieces to them, and we really have to work our way through that. So for our second topic, we'll get through from here all the way to example 5. And then our third lecture on this topic will deal with Kirchhoff's rules when we have multiple batteries, multiple power sources, or complex circuits. Okay. So please check that Canvas calendar, make sure you're on track, start doing some homework, keep up with the labs, meet me for office hours. All right, and we will stop recording. Bye.